Okay. Well, after having what I hope was a nice Thanksgiving break, you might not be ready to feel ready to be back in class. And trust me, I share that feeling. And yet here we are. But at least there's only 2 more weeks of suffering through class, and then the ultimate suffering of finals.
Then sweet release.
Yes. And actually, you all go for Christmas break in 3 weeks' time because you have 3 weeks from today is when final grades will be turned in. Then you all off on break, and I still have to do stuff. So, okay. So a week ago, I started this section. That's plenty of time for you all to think about all this on integrals over surfaces. So what I have for today is this number of examples. So if you're given a surface S that's described by parametric equations R of u v, which has components x, y, and z, all of which are functions of u and v. And u and v come from some two-dimensional domain. It could be any two-dimensional domain, usually a rectangle, but maybe a circle or some other shape. And from a description of a surface, we need partial derivatives of your parametric equations with respect to both u and v, and we put them into vectors, r sub u and r sub v. And from these, we have our normal vector, abbreviated n, and that is just the cross product of ru and rv. So these are things that we need to evaluate any kind of integral over a surface. So then there are 2 formulas. When your integrand is a scalar valued function, we have the integral of some scalar valued function little f over a surface S, and that just turns out to be a double integral over the parameter space. Let's do that. Okay. So whatever domain you have your parameters is a domain you're integrating over. And you have your integrand with your parametric equation substituted in for x, y, and z. And then you have the magnitude of your normal vector. And you integrate that with respect to your parameters u and v. And then you have the other possibility, which is actually of greater interest to us. If it's a vector field, so the integral of a vector field, capital F, that is also a double integral over a parameter space. You take your vector field and substitute your parametric equations, and you take the dot product of that with your normal vector and integrate that with respect to u and v. And for this formula, you let f equal 1 to give you the area of your surface. Okay. right, so now for the agenda for today is to use both of these formulas in a number of examples. Okay, so we have, suppose that S is a surface that's called a helicoid, and has these given parametric equations. X is equal to u cosine v, y is equal to u sine v, and z is equal to v. Now, these first equations for x and y, it's basically polar coordinates. So, but it's just instead of r and theta, we're using u and v. So we'll let u vary between 0, 1, and v between 0 and, okay, this example, pi. So u is playing a role of our r, and v is playing a role of our theta. So if we just looked at x and y, what we would get is the top half of the unit disk, and we would get all of this. Okay. But that does not take into account z. Z is equal to v, so the height of any of these points is equal to whatever your angle is. So if we were to look at this in 3 dimensions, then at this part we have a height of 0, but as we move around the xy plane, so your angle, which is v, is increasing, you start to get more and more height. So by the time you get to pi, your points have a height of pi, because everything's related. So basically, if v were to continue increasing past pi, you'd see this spiral, like a spiral strip. So it'd be kind of like a spiral staircase, or more like a spiral ramp that's twisting around the positive z-axis. Okay. But because we only limit v from 0 to pi, we just don't really have that much of that yet. Okay. But sometimes it can be helpful to focus on just a couple of coordinates, like only x and y, to get some idea as to what the surface looks like. Now, the problem in this example is compute the integral, and actually, what I should have done over here, since surfaces you can think of as 2-dimensional entities, these really should be double integrals. So integral over this surface of a function 1 plus x squared, square root of 1 plus x squared plus y squared. So this is our function little f of x, y, z. It just happens to not depend on z. Okay. Now, here we have our limits for, because we're going to change this to an integral with respect to u and v. At least the limits are given. But now we need to compute our normal vector, because you always need that in whatever formulas. In the first case, you only need the magnitude, and in the second case, you need it for a dot product. So we need to take our parametric equations derivatives with respect to u and v. So what would those derivatives be with respect to u and v? So first with respect to u. Cosine v. Yeah, 0, because the z part does not depend on u at all. And then down here with respect to v, yeah, minus u sine v, u cosine v, and 1. Okay, so now we need to take the cross product of these to get our normal vector. So you would cross multiply, so sine v times 1 minus cosine v times 0. So our first component is only sine v. Then the second component would be 0 times minus u sine v minus cosine v times 1. So that would give us cosine v. And then the third component we'd have u times cosine squared v minus a minus making a plus u sine squared v. So we'd have here it'd be u cosine squared v plus u sine squared v, which is just what?
2u.
U. 1u.
1.
Yeah, because you can factor a u out, and that is 1. Yeah. Okay, so that is our normal vector. Now, since we're integrating just a scalar valued function, this is not a vector field, over a surface, we only need the magnitude of this normal vector. So this is RU cross RV. So now the magnitude, we're just going to take a square root of the sum of squares of all the components. And again, cosine squared plus sine squared equals 1, so we just get square root of 1 plus u squared. So you can think of that as being like the extra factor that goes into our integral. So now we can finish setting up the integral. So the integral of this given function, 1 plus x squared plus y squared, over the surface, is now going to be an integral with limits from u and v. So we have 0 to pi in v, 0 to 1 in u, and then we have to express this in terms of u and v. So you have to substitute your parametric equations. So I'll fill those in. U cosine v squared plus u sine v squared. And then you have a magnitude of your normal vector that goes there. And we have that's down here. So okay, how's this going to simplify? So once you carry up the squaring.
1 plus u.
What?
1 plus u.
1 plus u squared. Yeah, because u also gets squared. So you have 1 plus u squared from here, and then you have this is also square root of 1 plus u squared du dv.
So the square root's going to disappear.
Yeah. So we get 1 plus u squared du dv. And now, in this case, the integrand only depends on u, and we have constant limits. So you can express this as integral of 1 dv and then 1 plus u squared du, and then finish it off from there. Because this first one is just going to turn out to be pi. So if you work it out to its conclusion, its examples on pages 135 to 136, and you get 4 pi over 3 for a final result there. Okay. But as with the integrals in the previous chapter, the major challenge here is the setup. And because your integrand is not a vector field, it has a single component, that's how you know it's just the first formula that's supposed to be used. And then getting your integrand in terms of u and v, getting your normal vector, which happens no matter what, and then its magnitude here. So are there any questions about setup? Okay.
Does it say page 135?
Yeah, 135, 136. Now, I should mention, so one application of this kind of surface integral as we talked before about center of mass. So if you have center of mass of a sheet S. So you have some generic warped sheet that has a shape of has a shape defined by S, it's parametric equations. So you have three components: x bar, y bar, z bar, that define the center of mass, and x bar is equal to the integral over the surface, and your integrand is x times a function rho of x, y, z, where that is the density of a surface of a sheet S at any particular point. Y bar and z bar are similar, but I need to include a factor here of 1 over m. So m, that is the mass of the sheet, and that is the surface integral of just the density. Okay, so we've seen these integrals before, where you give it some density function, you integrate the density over the object to get its mass equals density times volume. And then when we take the density and multiply by x, y, or z and integrate that and divide by the mass, it's like you're basically getting an average x component over the whole surface, where the average is weighted by the density. So the more density portion of the surface has, the greater weight those points get. So the average x, y, and z components, in this sense, make up the center of mass. Alright, so next I want to do some examples involving the other formula, the one I erased a little while ago, the surface integral of a vector field. And if you haven't already, you should look on the site for the practice final. You can see what formulas are there. So like both of these formulas for surface integrals will be on the formula sheet, just to know which one to use in which situation. Okay. All right, so now it's given that your surface S is part of a cone. Z is equal to square root of x squared plus y squared. You've seen this at least once before. So when you just have z equals x squared plus y squared, that's a paraboloid. But when you throw the square root in there, that makes it a cone. As a part of this cone below the plane, z equals 1. So what this surface looks like So here's your cone. And it's cut off at z equals 1. So it starts at the origin and makes it all the way up here. Okay. And very important, it must have downward orientation. And you'll see that when you're dealing with a surface, so in general, for a typical surface, at any point in the surface you have this normal vector n that is perpendicular to whatever tangent plane you have at this point. But how do you know whether you want this normal vector or this normal vector? So if this is n, then this vector would be minus n. How do you know which is the right one? So it's up to the problem to specify. So for instance, clearly this one would be upward orientation and this one would be downward. So once we get the normal vector, you'll find it's actually easy to tell whether it's upward or downward orientation, and if you get the wrong orientation, how to fix it. All right. Because if you get the orientation wrong, your integral is going to have a wrong sign. Okay. So the problem in this example is to compute the integral over this surface of this vector field f. And the vector field is x, y, and z to the fourth. Okay. Now, what we need are parametric equations to describe this surface. So we need x, y, and z as functions of our parameters u and v. So to get an idea as to what we should use, first of all, we have x squared plus y squared. That's a tip-off that you should use something along the lines of polar coordinates. Also, if you were to look down on this surface, this cut-off cone, so looking down the z-axis, what would it look like? Based on the picture.
Circle.
Yeah, it's going to be a circle. And even if you don't have a picture, you can tell by intersecting these two. So at the intersection, you have z equal to square root of x squared plus y squared, and you also have z is equal to 1. So now you can just take a look at this. So you have x squared plus y squared is equal to 1. You can tell that way it's a circle. So when you have multiple equations like this determining your surface, it's a good idea to equate them to understand, to see, because that's how you see it can often be described as intersections of one or more surfaces, like this cone and this plane. That marks this boundary here, where the two are equal. Okay, so that suggests using polar coordinates, at least for x and y. So you can let x equal to u cosine v, and y is equal to u sine v. And since we're dealing with a disk of radius 1, or the intersection is a circle of radius 1, that suggests that u goes from 0 to 1. So that comes directly from this equation right here. That defines the extent of your surface. What about v? V is playing a role of the angle here. It's like theta. So what should its bounds be? Yeah, it's going all the way around. There's no other surface here to restrict it. So we go from 0 to 2 pi. Okay. Now, what about z? Well, z, the surface is a part of a cone. It's defined by this equation right here. So use this. Z is equal to square root of x squared plus y squared. And you fill in what x and y are. But that's just going to simplify to what? Well, in polar coordinates, what is this anyway? That's r. But what variable is playing a role of r here? No. Instead of r and theta, we have u and v. Which one is playing a role of r? U. Yes, that's not. So you could work this out and simplify it. Bless you. Or you can keep in mind that based on how u and v are used here, that this is going to be like your r variable. This is going to be u. And like on a test, or whatever, you can use r and theta. I don't care. As long as you're consistent. Okay. So now we have parametric equations: u cosine v, u sine v, and then u. So now we can go ahead. Actually, it's almost the same parametric equations as the last example, except in that one, z was equal to v rather than u. But that still creates a completely different surface. Okay, so now we need our vectors, ru and rv, partial derivatives of your parametric equations with respect to u and v. So with respect to u, what do we get? Cosine v and 1. Okay, and then for with respect to v?
Negative u sine u cosine v. And
0, because z does not depend on v at all. Okay, now you take the cross product of these, so your normal vector, which is ru cross product rv. So we take sine v times 0 minus u cosine v times 1. 1 times minus u sine v minus cosine v times 0. So that's minus u sine v. And finally we have u cosine squared plus u sine squared. You simplify all that, and what you get is u. Now, so you keep in mind, so what this is saying is that at any particular point on this surface, identified by parameter values u and v, this vector is perpendicular to the surface. But we want it to have downward orientation. If a vector is pointing down, then what does that say about the z component?
It's pointing like left.
What?
It's pointing left or right
Um,
on a different
well,
axis.
if we forget x and y, focus only on the z component, because z indicates up or down. So what should be true of the z component if a vector is really pointing downward in any sense? I don't necessarily mean straight down, but down at all.
negative.
Negative. Is that what we have here?
Oh, yeah. Two negative.
But only the z component. Yeah, because we have to look at the values of u that we're going to have between 0 and 1. So what will happen is the vector that's computed over there is going to be pointing this way, upward. So it's not the normal vector we want. So this is the upward orientation. Now, that's because by convention, we do RU cross RV. If we'd gone the other way, RV cross RU, that would have negated this. But now that we know we want downward orientation, but we got upward, we're going to use the negated normal vector. So that will be U cosine V u sine v, and minus u. So this has downward orientation. So when we take our dot product in our integral, which we're going to set up in a second, that is the normal vector that will fill in. Or what we could have done was just gone ahead and used this, finished the whole problem, and then we had to remember to change the sign of the answer at the very end. Yeah. So however you want to do it. But make sure the orientation that's prescribed is taken into account. Now, for the other kind of problem, the previous example of integrating a scalar value function over a surface, orientation doesn't matter for that kind of problem because we're only taking a magnitude of a normal vector, which is not going to be affected if you negate it. But when it's a surface integral of a vector field, then it matters. So now we can set up the integral. Alright, so we have our limits in u and v. So v goes from 0 to 2 pi. U goes from 0 to 1. And then we have x, y, z to the fourth. That's our given vector field with the parametric equations to be plugged in. Dot product with the normal vector, and so that'd be u cosine v minus u for downward orientation d u dv. Okay. So the last thing to do in a setup is we need to substitute parametric equations in.
Is that to the fourth power?
Yeah, because that's the given vector field over there, x, y, z to the fourth. So x is u cosine v, y is u sine v, and then z is just u, so it's u to the fourth. Dot product with u cosine v, u sine v, minus u. Okay, so now this is a dot product, so we multiply corresponding components and add them up. Okay, so we're going to get u squared cosine squared b plus u squared sine squared v minus u to the fifth. Okay. So that is your integrand, which can be simplified to what?
U squared minus u to the
Yeah,
fifth.
this condenses to u squared. If you can factor u squared out of these two terms, then you get, it seems to
Squared
happen all the
times
time,
1.
cosine squared plus sine squared equals 1. Also, after that, there's no dependence left at all on v in the integrand. So we end up getting pi over 3 for final result in that case. Okay. Are there any questions about this one, especially how it was set up? Okay. In certain cases, you can, so just for other examples, simplification is possible. if S is defined not by parametric equations, but as a graph, Z is a graph of a function of x and y, then your parametric equations are x is equal to u, y is equal to v, and then z is equal to g of u and v. And that's going to simplify computing the normal, because you have Ru is going to be derivatives of all of these with respect to u. So that's 1, 0, gu. And then Rv is equal to derivatives of all of these with respect to v. So it's 0, 1, gv. So then the cross product works out much more nicely. So your normal vector turns out to be minus gu minus gv 1. Or you can think of this as, if you keep everything in terms of x and y, minus gx minus gy and 1. So what you can do is, you don't have to go through parametric equations in this case. You can take this description and jump directly to using this as the normal vector, and then setting up your integral from there. Save yourself a little time. Now, this example is going to be, well, it's not something I would be able to finish here. And it's on the notes, but at least I can get the ball rolling and give you the main ideas on how to do it. Because sometimes surfaces come in more than one piece. All right, so suppose your vector field is y, z minus y, and x. And your surface S is the tetrahedron with these vertices: the origin, and then the vector I, 1, 0, 0, j, and k. So I go one unit along each with positive x, y, and the z axes. And the problem here is to compute the integral over this surface of this vector field. So you're going to have to compute the dot product of f with the normal vector. Now, what makes this example a real pain is, in order to describe a tetrahedron, the tetrahedron has 4 faces. So you're going to need 4 sets of parametric equations. So here's the base. So here's your origin. Here's one of your vertices, 1, 0, 0. Here's another, 0, 1, 0. And then you have a vertex up here, 0, 0, 1. So the idea is, you come up with parametric equations for each of the 4 faces, evaluate that integral over those 4 faces, and then you add them all up. We assume positive, which in this case means outward, orientation. Because S, a tetrahedron, this is the first example today where the surface is a closed surface. It's enclosing a solid. So when we say positive orientation, we really mean that the normal vector should be pointing outside of a tetrahedron, not into it. Okay, so since we have 4 faces, I need to label those 4 faces. Okay. So our first face, we'll take a side view. So this is the z-axis, and here we're looking along the x-axis. So the y-axis is going into and out of the board. So I'll call this S1. So to come up with parametric equations, we need equations for x, y, and z, all being functions of u and v. Now, S1 is this face over here. Well, that face is entirely contained within the plane y equals 0. So if I want to make my parametric equations, x, y, and z, well, why is this going to be 0? So at least for each of these faces, one of the variables is going to be trivial. And then I can describe z as a function of x because I have z of this boundary is equal to z is equal to 1 minus x. That describes this line segment here. So what I can do is I can let x be equal to u and then z be equal to v because I can describe this whole face using only two of the variables, x and z, so I'll just make those my parameters. The only thing I have to be careful about is describing the proper bounds for u and v. So u, which is x, would go from 0 to 1. It's like when you're setting up double integrals. It's the same principle. V corresponds to z, so what should the bounds be in this case? To describe this face, this triangle.
Is b gonna be between 0 and 1?
Well, it starts at 0.
So 1 minus x?
1 minus x, which in terms of u and v is 1 minus u. Yeah. So this describes my region D, my parameter space. So u and v don't always have constant limits. We like when that happens because it's easier for the integral, but it can be any two-dimensional region D. So these are my parametric equations for S1. So now what you can do is compute your normal vector, RU and RV. So we differentiate these with respect to U and V. So we get 1, 0, 0 in this case. And then we have, with respect to V, it's going to be 0, 0, 1 in this case. So the normal vector, we take the cross product of these and we get 0. Then we get 0 minus 1. And then 0. Now, since this is a vector I and this is a vector k, you can expect that you're going to get the vector either j or minus j, because it's the only vector that's orthogonal to both of them. But the thing to pay attention to is this vector pointing outside the tetrahedron? Because that vector n is going this way. Because positive y-axis is this way, negative is this way. And yes, this is the orientation we want. So this is outward. So we don't need to negate it. So now, the surface integral over just this face, S1, of my vector field. Okay. We have our limits from here. So 0 to 1 in U, 0 to 1 minus U in V. And then we have our vector field, which is y, z minus y, and x, dot product with our normal vector, 0, minus 1, 0, d, v, du. The only thing left for the setup is I have to express this in terms of u and v. I have to use my parametric equations. So y is 0, z is v minus 0, and then x is u. So now everything is expressed in terms of u and v, and from a dot product, what's nice is we have these components that are 0. So I have to multiply corresponding components and add them up, and the only one I'm going to get is minus v dv du. So now this integral is ready to evaluate. It's all what?
We can separate the du and pull it to the
Um,
value of 0 to 1, right?
No, we can't separate these because of a limit here. Yeah. So constant limits go right ahead, but on this case. And if the result turns out to be minus 1/6, gory details are on page 140. But the thing is, this has to be done 4 times over because that was just one face. So you'd have a face like the base of a tetrahedron where z equals 0, and your normal vector should be pointing down, like 0, 0, minus 1. And then x and y would be u and v with the appropriate limits. That would be similar to this. This face in the back, also very similar, but just dealing with y and z instead of x and z. So 3 of the faces are very similar. The only one that's more significant is the top face. And I'm probably out of time, aren't I? 2 minutes. Okay. So S4, the top face, what do you do in that case is you can, if you're looking from above, it still looks like this triangle in the xy plane. So you let x be equal to u, y be equal to v, and then the plane is z is equal to, the plane is equal to x plus y plus z is equal to 1. That's the defining equation of the top face of the tetrahedron. So z is equal to 1 minus u minus v. And then your parametric equations come from here. U goes between 0 and 1. V goes between 0 and 1 minus u. And your normal vector is, if you take the partial derivatives and work all that out, you get 1, 1, 1, which are the coefficients from the equation of a plane. And that is the correct orientation. It's pointing outside the tetrahedron. Again, I would encourage you to look at the details that are in the notes to see how all the faces are done. No, I would not give a problem this long on a test, unless there's a bonus or something, which I'm not above doing. But these are good examples, each face individually, about how to properly set up a surface integral. Okay, so Stokes theorem on Wednesday.